Hello everyone and welcome back to the module 2. We had been discussing about the design and implementation aspects of loaders and linkers, and we had started the discussion on this module with the basic loader functions, wherein we have seen the design and implementation aspects of a simple absolute loading scheme. Thereafter, in the previous lecture, we have examined the machine dependent extensions to basic loader functions, and we have discussed the issues of program relocation from loader's point of view. In the upcoming two sessions, we will discuss the issues of program linking by first reviewing it from the perspective of assembler and thereafter from the perspective of a loader. In this process, we will discuss the design and implementation aspects of linking and relocating loaders. The concept of program linking was first introduced in Module 1 under control sections, while machine independent features of assemblers were discussed. And you are already aware that segments of the program that form logical subdivisions or segments representing subroutines could be assembled independently by the assembler. And we had referred to such segments as control sections. However, when control sections form a logically related parts of a program, it's common for instructions in one control section to refer to instructions or data located in another control section. So some means of control section linking is necessary. However, as control sections can be independently loaded and relocated, assemblers are generally not able to process these references in usual way. So the resolution of external references between control sections could only be delayed and performed by the loader. We refer to such references between control sections as external references. And the assembler generates information for each such external reference, which will allow the loader to perform the required linking. In our earlier discussions on control sections, we have also seen that symbols that are defined in one control section cannot be directly used by another control section. That is, they must be identified as external references for the loader to handle. And we have discussed two assembler directives used for identifying external symbols in the assembly language source program. The two directives were xdef and xtref. While xtref identifies those symbols that are defined in the current section, control section, that can be used by other control sections, xref identifies those symbols that are used in the current control section but defined in other control sections. In understanding the concept of program linking, in module 1 we had taken an example program containing 3 control sections, namely main, added and subtract. And we had seen how each of the control sections are independently assembled by the assembler. During pass 1, the assembler maintains a separate location counter for each of the control sections, which are initialized to zeros at the beginning of the assembly. And during the pass 2, instructions involving external references have been assembled using the 4-byte format or using the extended format, wherein the direct address of the operand is used in assembling the instruction. And whenever the operand involves a reference to an external symbol, as a value for the external symbol is not known to the assembler inserts a value 0. Further, we have seen that whether the assembler assembles the control sections together or separately. Each of the control section will appear in each of these control sections would appear as separate segments of the object code. That is, after the assembly, they will appear as separate control sections. You may see that each of these represent independent object programs generated for the control sections main, added, and subtract. Further, in order to enable references between the control sections, in the object program, define and refer records have been used, which identify those symbols defined in and referred to the corresponding control section. Also, further modification record has been employed by the assembler to instruct to the loader other information that is required for program linking. In today's discussion, we will consider complex examples of external references between programs, and we will use these examples to examine the relationship between relocation and linking. Further, in this process, we will also discuss the design and implementation aspects of linking and relocating loader, which is an advanced loader typically found in most modern computing systems. To begin with, we consider three source programs written in assembly language for SICXC, namely Program A, Program B, and Program C. Each of these programs are separately assembled by the assembler, and you may see that each program, Program A, Program B, Program C, consists of single control section. Each of these contains a single control section, and each program contains a list of items, namely list A, list B, and list C. It has list A in program A, list B in program B, and list C in program C, with the ends of the list marked by the labels NA, NB, and NC. Also, the labels on the labels representing the lists, that is list A, list B, list C, NA, NB, and NC, are external symbols in the sense they are available for use in linking. You may see that in program A, we have the labels list A and ND. List A and ND are defined in program A, and these have been listed using the directive xdef, meaning that though the symbols are defined in the section program control section programming, they are available for program linking, or these symbols can be used in other control sections. Likewise, list B and NB are defined in program B and are identified as external symbols using the directive xdef, meaning that the symbols are available for linking, and these symbols can be used in other control sections. Same applies to list C and NC. Further, you may also notice that each program contains exactly same set of references to the external symbols representing the labels list A, list B, list C, NA, NB, and NC. So some of these references appears as instruction operands, while others appears as values of data words. So we have represented or marked those external symbols that appears as instruction operands explicitly as reference 1, reference 2, and reference 3, while the external symbols that appear as values of data words are marked as reference 4 through 8. So you may see that each program has exactly same set of references to the external symbols. For example, this is program A. You may see same set of reference in program B and in program C. So as I mentioned, some of the external symbols appears as operands for the instructions, while others are values of data words. That is, reference 1 through 3 are instruction operands, while reference 4 through 8 are values of data words. And in our discussions, we will focus only on the issues of relocation and linking. And that is why portions of the program that are not involved in relocation or linking process have been omitted, or we have indicated them with dots. So all portions of the program not involved in relocation and linking process have been omitted, which also applies to the object program that is generated. Now, examining each of these programs, program A, program B, and program C, you may see that apart from the symbols defined in the section, certain symbols have been identified using the directive xref. So these are symbols which are referred to in the control section but are defined elsewhere or defined in other sections, such as, for example, in program A, list B and B, list C and C are external references, meaning that they are defined in other sections. Likewise in program B and C. Now, to understand the issue of program linking, we will first examine how external references are handled by the assembler. And we will examine this by considering pass 1 and pass 2 processing for each of the programs A, B, and C. So pass 1 has to do with assignment of address to every instruction, and as each of the programs are independently assembled, the initial location counter values are set to zeros for each of the programs, program A, B, and C. Further, you may notice that the instructions have been assigned with the addresses, or each labels in the source program has been assigned the address. We assume that list A and NA respectively have the address 40 and 54. Likewise, list B and NB are assigned the address 60 and 70, while list C and NC are assigned the address 30 and 42. Likewise, all the other labels, that is reference 1 through 8, have been assigned the address. For example, in program A, reference 1 is assigned the address 20, and depending on the length of the instruction that is labeled by reference 1, the addresses are assigned to reference 2 and 3. Likewise, address corresponding to reference 4 is 54, and depending on the length of the constant generated, addresses are assigned to reference 5 through 8. And this applies to every control section, that is to every program, program B and program C as well. So with the assumption that each instruction has been assigned with the address during pass 1, we will now carefully examine the pass 2 processing of each of the programs A, B, and C, and we will see how each of the references are handled within the 3 programs in different ways by the assembler. We'll first begin by considering reference 1. For the first program, that is program A, reference 1 is simply a reference to a label which is defined within the program. We have a reference to the symbol list A, and list A is defined within the program A. So since the symbol is defined in the same control section or the same program, the instruction can be assembled in a usual way using relative mode of addressing. And in this case, you may see that the program counter relative mode of addressing has been used to assemble the instruction. And since we use the relative mode, no modification record is necessary. You may see that the instruction is assembled with the 12-bit displacement, where displacement is computed as the address of list A minus the program counter value, which is respectively 40 and 23. So the displacement is 40 minus 23, which is 2D. The first byte is obtained by adding 3 to the opcode. Opcode for LDA is 00. We need to add 3 to the opcode because the instruction indicates neither indirect nor immediate mode. So N and I are both set to 1 and 1. And the flags X, B, P, E are set to 0010. Thereby, the third half byte here indicates 2. Consider the same instruction or the reference in program B now. So in program B, the instruction involves a reference to symbol list A. However, list A is not defined in program B. So it is identified as an external reference using the directive xref. You may see that it is an external reference. That is, the symbol is used in program B, however, not defined in program B. It is defined in some other control section. So since this value is not available in the current control section, program counter relative or any relative mode of addressing cannot be used. That is, we cannot compute the displacement and assemble the instruction. Hence, the assembler uses an extended format or the 4-byte format with the address field set to 0 because the address corresponding to list A in program B is not known. Further, having assembled the instruction with 0 in the address field, the assembler needs to place a modification record in the object program for program B, instructing the loader to add the value of the symbol list A to the address field when the program is linked. So, to summarize, for the reference marked 1 in program B, the assembler uses an extended format and assembles 0 as a part of the instruction in the address field. And it includes one modification record in the object program for program B, instructing the loader to add the actual value of the symbol list A to the address field when the program is to be linked. This reference, that is reference 1, is handled in the same way for program C as well because list A is defined in program A and not in program C. Again, list A is an external reference in program C as well. So similar handling proceeds in program C as well for the reference list A, that is reference 1. So the object program for program C corresponding to this instruction should include a modification record indicating the loader to add the value of symbol list A to the address field when the program is linked. So to summarize, in program A, reference 1 is simply a reference to a label which is defined in the same section. Hence, program counter relative mode can be used and the instruction can be completely assembled. No modification record is required. In program B and C, reference 1 is a reference to an external symbol. Instruction involves reference to a symbol defined in other section. Hence, the instruction is assembled using the extended format with the address field set to 0 and to enable actual value of list A to be added to the address field. Modification record is used to instruct to the loader the necessary modification that is to be done, that is to add the value of list A when the program is linked. Now we will proceed ahead with the processing of reference 2. The reference that is marked reference 2 will be processed in the same manner. So in program A, for program A, the expression, the operand expression for LDT consists of external reference plus a constant. Constant here is 4. So as the value of list B is not known to the assembler when program A is assembled, because list B is not defined in the current control section, the assembler stores the value of the constant in the address field of the instruction, and it includes a modification record in the object program for program A, directing the loader to add to this field the value of list B. So you may see that the relative mode cannot be used here, and the instruction needs to be assembled using the 4-byte format. And the last 20 bit in the 4-byte format is the address field, and the address here should correspond to list B plus 4. However, since list B is an external reference, the assembler assembles the address field with the value of the constant 4. But since list B needs to be added, it leaves a modification record in the object program for program A, directing the loader to add to this address field the value of list B. Now moving on to program B. The same expression in program A is handled in a different way because list B is a symbol defined in the same section for program B. So it is simply a local reference, and the instruction can be assembled using program counter relative mode. So no relocation or linking is necessary here because we use the relative mode of addressing. And you may see that the program counter relative mode is used, and we compute the displacement as the target address of the operand, that is list B plus 4, which is 60 plus 4, minus the PC value, which is 3D. So we have the displacement 0 to 7, which is represented in the 12-bit field. The first byte is 77, which is simply 74, which is opcode for LDT, plus 3, as N and I both are set to 1 and 1. And since we use a program counter relative mode, XBPE should be set to 0010. The reference marked ref2 in program C is handled in same way as it was handled in program A, because list B is an external reference to program C as it is an external reference in program A. So it is handled in the same way as it is handled in program A. So to summarize, since reference to involves a reference to the label list B in program B, which is a local reference, the instruction can be assembled using relative mode of addressing in program B. It can be completely assembled and no modification record is required. While in program A and C, the reference to the symbol list B is an external reference, and hence the assembler is not able to completely assemble the instruction because value for list B is unknown, and hence it assembles the instruction using the constant value plus 4 that is provided as a part of the expression defining the operand. And since the value of list B is not assembled as a part of the instruction at the assembly time, a command is placed in the object program via modification record, indicating to the loader that the actual value of list B has to be added to the address field when the programs are linked. We will now consider ahead with the processing of reference 3. Reference 3, as you see in program A, is an immediate operand, and the value of the operand is the difference between NA and list A. So you know that NA marks the beginning of the list while NA marks the end of the list in program A. So NA minus list A simply represents the length of the list in bytes. So now to assemble this instruction in program A, the assembler has all information that is necessary to compute the operand value. So the operand value could be computed as NA minus list A, which is 54 minus 40. So we have LDX hash 14, and 14 is an immediate operand which is assembled as a part of the instruction. You may see that we assemble this as a part of the instruction. The first byte is obtained by adding 1 to the opcode. We know that LDX is 04. We need to add 1 because the mode here is immediate. That is, I has to be set to 1 and N is 0. So N and I are 0 and 1 respectively, which is same as adding 1 to the opcode 04. And XPPE are respectively set to 0, 0, 0, 0 because we don't use relative mode, we don't use indexed mode or extended format. And the value of the operand is explicitly encoded as a part of the instruction. So consider the same reference in program B and C. While assembling program B and C, you may notice that for this instruction, the values of labels are unknown because NA and list A, as you see, are external references in program B. Likewise, these are external references in program C. That is, their values are not known at the time of assembling program C and program B. Hence, the expression must be assembled as an external reference with two modification record. Although the final result will be an absolute value independent of the locations at which the program is loaded. So you may see that the instruction is assembled as an external reference because since these values are not known at the assembly time, we can't use relative mode of addressing here to assemble the instruction or the immediate mode, the immediate value here, because both values are unknown, which can be estimated only at the time of program linking. So in the so the 4-byte extended format is used, wherein in the address field we insert zeros because both NA and list A are unknown in program B as well as in program C. The first byte is obtained as in the case of program A. It is just 04 plus 1 because 1 is to be added because I is set to 1. And since we use the extended format here, E has to be set to 1. That way the third half byte here is 1, which is 0001. It is XPPER respectively 0001. So to summarize, in program A, reference 3 is simply a reference to a label, to two labels which are defined in the same section. Hence, immediate operand value could be used. We can estimate NA minus list A, and the resultant value could be used in assembling the instruction. However, in program B and C, and A list A are external references. They involve reference to external symbols which are not defined in program B or C. Hence, the instruction needs to be assembled using the 4-byte extended format with modification record in the object program indicating the loader to add the actual value of NA to the address field. Likewise, subtract the value of list A from the address, from the field at the indicated location, that is indicating the address field of the instruction. The following statements are indicated with dots, meaning that they are not of importance in our discussion here because they have nothing to do with program relocation or linking. So we will skip those statements, and then after that we have this instruction LDA EQU star, sorry, list A EQU star and A EQU star. So these instructions are assembler directives, and so no object code needs to be generated at this point. And the same applies in other programs as well. Program B also defines symbols list B and NB using EQ statement. And so no object code needs to be generated as they just define symbols list B and NB. Likewise in program C, where list C and NC are defined. Please note EQU has operand star, meaning that the value for list, the labels are the current location counter values, and the values are assumed here for each of the control sections. We will now consider processing reference 4. For program A, reference 4 can be evaluated by the assembler except for the value for list C. because you may see that reference 4 through 8 are values of data words, and the values of data words here are given by expression. For example, reference 4 is given by the expression NA minus list A plus list C, which involves terms that are external symbols. In the expression, NA and list A are known in the control section program A, because NA and list A are defined in the same section. However, not list C, because list C is defined in program C. So while this instruction is assembled, the assembler cannot evaluate this expression completely, as the value for list C is not known. However, NA and list A can be used in partially evaluating the expression. So the assembler for program A can evaluate the expression in reference 4 except for the value of list C. So this results in an initial value of 0000014 in programming, which is simply NA54 minus list A, which is 40. So it is just 000014. So you may see that since the directive here is word, one word is equal to 3 bytes. So we represent the constant in 3 bytes. That is 14 has to be represented in 3 bytes. However, since the complete expression has not been evaluated, that is the value for list C is not known, one modification record is required indicating to the loader that the value of list C has to be added to the current value, that is to the value 000014 at the time of linking, and the relative address where this value is placed in the memory is 54. Now we will consider the same reference in program B and C. So in program B, we may see that the whole of the expression cannot be evaluated because none of the terms are defined in the same section. And list A and list C, none of these symbols are defined in the control section program B. Hence, the object code generated will contain an initial value of 0 because none of these values are known, and the object program for program B for this instruction should contain 3 modification records. One indicating the value of NA to be added, the second indicating the value of list A to be subtracted, and the third indicating the value of list C to be added. We'll consider now the processing of reference 4 in program C. For program C, since list C is defined in the same section, the assembler can now supply the value or use the value of list C. However, the value of this list C is relative to the beginning of the control section program C. That is, the value here is 0030. This is just a relative value in the sense that the value list C is based on the assumption that the starting address for program C is 0000. However, if the program is attempted to be loaded at a different location, the value for list C will be some other value, in which case a modification record has to be placed in the object program to indicate actual program starting address for program C to be added at the indicated location. So the initial object code generated will be the value for list C, which is 30, and the modification records generated will instruct the loader. We note that here we require 3 modification records, and these modification record will instruct the loader to add the beginning address of program C, indicating relocation, and add the value of NA and to subtract the value of list A. So the first two, adding the program starting address of program C, is actually an example for relocation, while adding NA and subtracting list A is an example for linking operation. So you may see that the expression in reference 4 actually represents a simple external reference in program A, because NA and list A are evaluated, only that is a reference to a symbol list C which is defined in another control section. So it involves a simple reference, external reference in program A. And in program B, it involves a program B, it involves a complicated external reference because none of the symbols are defined in program B. And for programs C, it's a combination of relocation as well as uh, external reference to a symbol defined in program C. So in programs in program A, one modification record is required indicating the value of list C to be added. In program B, 3 modification records are required because none of and A, list A and list C are known. So 3 modification records are required and the value assembled is 0. While in program C, uh, 2 modification records indicating linking, that is indicating the value of and A and list A to be substituted, while 1 modification record indicating the starting address for program C to be added at the location, indicating relocation. So this is an example for relocation as well as linking in program C. Uh, So reference 4 through 8, as I mentioned earlier, are values of data words, unlike reference 1 to 3, which are instruction operands. We will now consider processing reference 5. So reference 5 in program A involves references to 2 external symbols, NC and ListC. You may see that the instruction operand has 3 terms, NC, ListC and 10. Both symbols are unknown. However, since 10 is a constant, the initial assembled value will be the 2's complement for 10. So which is FFFF6. And 2 modification records are required in the object program indicating to the loader the value of NC to be added and the value of ListC to be subtracted at the relative location 57. We will consider the processing of reference 5 now in program B. Now in program B, the scenario is exactly same as it is in program A because NC and ListC are again external symbols in program B, and the initial value is obtained by assembling the value of minus 10, which is 2's complement of A, which is so initial value generated is FFFFF6, and 2 modification records have to be placed in the object program for program B, indicating the value of NC to be added and ListC to be subtracted. In program C, on the other hand, the entire expression in the operand field can be evaluated because NC is defined in the same section and likewise ListC. So NC minus ListC will give the size of the list in bytes, which is 42 minus 30, which is 12. And then we have a term minus 10. So 12 minus 10, 10 in hex size A. So it will give us a value 0008. Since the constant generated is represented in 3 bytes, so we need total 24 bits and the representation is 000008. So here the operand involves reference to symbols which are defined in the same section and hence can be completely evaluated. So no modification record is required for this particular instruction in program C. Now we will consider processing reference 6 with respect to program A, B and C. Reference 6 in program A involves reference to 2 external symbols NC and ListC, which are actually defined in program C. So these are external references whose values are not known as of now to the assembler during the assembly time. However, list A is a symbol defined in the same section and its value is known, and the expression has a constant term -1. So initial value is obtained by the assembler by computing list A minus 1. List A is 40, 40 minus 1 is 3F. So the initial assembled value is 00003F, which is represented in 24 bits. And since NC and list C has to be added and subtracted respectively, two modification records needs to be inserted in the object program for program A, indicating the value of NC to be added and the value of list C to be subtracted. Consider the same expression in program B. Now reference 6 in programs B involves a complicated external reference as none of the symbols are defined. However, the expression has a constant term, so initial value of the object code generated will be the internal representation for -1, which is 2's complement of 1. So 2's complement of 1, as you see here, is FF. So having generated this code in the object program, we need to have three modification records, one indicating the value of NC to be added, the value of list C to be subtracted, and the value of list A to be added. So three modification records needs to be included in the object program. Consider the same in reference 6 in program C. In program C, only list A is unknown, so the entire expression can be evaluated except for list A. So the value would be computed as NC minus list C, which is 42 minus 30. 42 minus 30 is 12, and we have a constant -1. So 12 minus 1 is 1. However, since list A is currently not known at the assembly time, one modification record has to be inserted in the object program, indicating that the value of list A has to be added at the field that begins at the relative address 48 to get the appropriate value. So one modification record would be required. We will now proceed with reference 7 and see how it is handled in program A, B, and C. So consider a reference 7 in program A. So the expression that defines the operand is given by four external symbols, AND A list A and AND B list B. Since AND A and list A are defined in the same section, this expression can be partially evaluated using the values for AND A and list A. However, AND B and list B are external references, so their values are not available. So the initial assembled object code is the value obtained by subtracting list A from AND A, which is 54 minus 40, which is 14. And in the object program, two modification records will be required, as AND B has to be subtracted and list B has to be added. So two modification records will be inserted in the object program for program A corresponding to this instruction, indicating that value of list B has to be added and AND B has to be subtracted. Consider reference 7 in program B. Now, in this case, unlike in the program A, where AND A and list were defined, in program B, AND A and list A are external symbols because their definition is not available in program B. However, AND B and list B is known. So AND B minus list B indicates the length of the list in bytes, which is 70 minus 60, which is 10. However, since here we have a negative sign, we have to take the 2's complement of 10, which is FF. So this is the initial assembled value, but since AND A and list A are not known, two modification records needs to be inserted in the object program for program B, indicating that value of AND A has to be added and value of list A to be subtracted. Finally, in program C, reference 7 involves a complicated external reference, as none of the symbols are defined here, because AND A and list A are defined in program A and B list B are defined in program B. We are currently in program C. So none of these symbols are known. They are all external references. So initial value is 0, meaning that none of the values are available. So having inserted the initial value 0 in the object program, four modification records have to be inserted, indicating that value of AND A has to be added, list A to be subtracted, the value of AND B to be subtracted, and value of list B to be added. So four modification records would be required. So that is all regarding processing of reference 7. Finally, we will discuss how reference 8 is handled in each of the control sections. So reference 8 in program A involves a reference to one external symbol list B. Value for list A is available in the same section. However, this value is a relative value, which is simply 0 plus the starting address, 40 plus the starting address, which is 40. So since this is just a relative value, the actual value for list A has to be obtained at the time the program is loaded into memory. So one modification record is required. Although value for list A is known, the value is a relative value. One modification record has to be inserted in the object program, indicating that actual value of program A has to be added to the field where list A has been placed. So since we have a negative sign before list A, it means that we have to subtract the starting address for program A in the corresponding memory location where the constant has been generated. Since list B is an external reference, one more modification record is required corresponding to list B. So the modification, the object program for program A will generate an initial value ff in the object program for program A. The initial value generated will be ffffc0, which is simply the 2's complement of list A, that is 40. 2's complement of 40 is ffffc0. And in the object program, two modification records has to be inserted, one for list B, as list B is an external reference, and second indicating relocation, because list A is a value relative to the beginning of program A, not the actual value for list A. As if we load the program at 5000, then the value for list A will not be 40 but 5040. So two modification records, one indicating relocation and the other indicating linking. Moving to program B, the instruction can be assembled using the relative value for list B as in program A. However, list A is an external reference. So initial value of list B is encoded, which is 60. However, this value is just a relative value with the assumption that starting address is 0. So one modification record is required to indicate that actual value of program B has to be added at the address 7C, allowing program relocation. Now coming to list A is an external reference. So one modification record has to be inserted in the object program, indicating that value of list A has to be subtracted at the indicated. Finally, considering this reference 8 in program C, none of the symbols are defined in the control section, hence it involves a complicated reference to symbols defined in other sections. So initial value is assembled as 0, and two modification records needs to be inserted in the object program, indicating value of list B to be added and value of list A to be subtracted. So that is all regarding the generation of the object code. So you may just go through each of these object codes and work out and see how each of the object codes are generated by the assembler. I suggest that you work in hand each of these object codes to get to know how each of the object codes are generated in different control sections in different manner. So having generated the object code, at the same time during pass 2, the object programs are generated. The object program, as you are all aware, contains header record, define and refer record, text record, modification records, etc. So we will see the object program generated for each of the control sections, program A, program B, and program C. So the length of program A, as you see here, is 63 bytes. We'll now see how to generate the object program using the object codes that were generated earlier and using the information regarding the modification record that I mentioned in the discussion earlier. So we will consider first the object program generated for program A. As the first instruction is processed, that is the start statement is processed, the header record is generated with the name of the program, the starting address, and the length. The program name is program A, starting address is the relative value 0, and this length of the program, as I mentioned earlier, is 63. So the header record identifies the name of the program, starting address, and the length, which is 63. Thereafter, the next instruction is xdef, which labels external symbols defined in program A, which are list A and end A. The values are respectively 40 and 50. These are relative values. So these will be entered into the defined record along with the symbol name and along with the symbols. So you may see the defined record. List A has been added and end A are added with the value 40 and 50. So the format is D followed by external symbol followed by the address of the external symbol, and this has to be repeated for every external symbol in the xdef statement. So in this example, you see that there are two external symbols, end A and list A, which are defined in program A. So having placed the defined record, next we in the source program we have xref statement, and corresponding to this we need to generate the refer record. So refer record simply lists all symbols in the xref statement. For program A, these are list B, NB, list C, and NC. And as you see, all of these symbols are placed one after the other in the refer record following the character R. So thereafter, the remaining instructions are not of much importance, and so we have indicated it with the dots in the in the source program. So likewise, it is indicated in the object program with dots here. Thereafter, the first instruction that is generated is corresponding to reference 1, and it is placed in the memory at the address 20, relative address 20. So the object code generated is 03201D. So this code has to be placed into the first text record with the starting address 20. So you may see the text record here, starting address is 20, and the first object code placed is 03201D. Please note this instruction does not require any modification record, as the program counter relative mode of addressing was used in assembling, and the instruction was completely assembled without any external reference. So 03201D is placed. Thereafter, the next instruction that is generated or processed is LDT list B plus 4. Already we have seen that in program A, since list B was not known, the instruction was assembled with the address field whose value is only the constant 4, and the modification record is to be placed into the object program. So corresponding to this instruction, the object code is placed in the current text record. So you may see that the object code is placed in the current text record. Also, one modification record is generated indicating that the value of list B has to be added at the address 24. So how did we get this 24? You know that the instruction LDT is placed starting from the relative value 23, and the opcode 77 will be placed in 23. The address field will begin in the memory at 24. So that to the address field, which initially contains the value 4, we need to add the value of list B. So that way the modification record indicates that to the address field that begins at the address 24, which is 5 half bytes in length, add the value of list B. Proceeding ahead, the next object code generated is 050014, and please note here there are no external references, as end A and list A are defined in the same section. We have already seen this. So this object code can be immediately placed into the text record without the need for any modification record. So the object code has been placed. We will proceed ahead now. After that, we have a series of instructions which are not a part of program linking and relocation. So we'll just ignore those statements and consider the next object code, which is generated here corresponding to reference 4. So the object code generated is 000014, which has to be, since there are a few set of instructions here, we can terminate the previous text record which contains 050014. So you may see we have stopped this text record, and the length is 3 plus 4 plus 3, which is 10 bytes, which is 0A. So now having processed the reference 4, the object code generated is 000014. This was already explained. And how did we get this 1,4? It is NA minus list A. But value for list C was not known. So one modification record has to be inserted in the object program saying that to the field that begins at 5,4, we need to add the value of list C. So you may see that the modification record is added here. To the field that begins at 5,4, add the value of list C. The field is 6 half bytes in length. Why is it 6 half bytes? Because this represents a constant which is 3 bytes in length, and 3 bytes is equal to 6 half bytes. The code itself is placed in the text record that follows. See, we have terminated the previous text record and the new text record is written with the starting address 5,4, because object code after this point begins here with the address 5,4. So 5,4 and the code is 1,4. Corresponding modification record is indicated. Next, moving on to reference 5, the object code generated is FF, FF, F6, which corresponds to -10. NC and list C were unknown. So for these two modification records are required, indicating the value to be added and subtracted at the location 57. So two modification records indicating modification at the location, relative location 57, value of NC to be added and list C to be subtracted. The object code FFFFF6 has been placed in the text record immediately following 1,4. So immediately following 1,4, we have placed FFFF6. Next, moving further, the next is reference 6 and the object code is 00003F. So in this case, again, only the value -1 was assembled, and there are two external symbols, and the value of list A, although known, is a relative value. Its value is not the actual value because we have assumed that the program A begins at 0, which is not necessarily the case when the program is loaded. So two modification records indicating the linking and one indicating relocation has to be generated. So the address is 5A. So at the location 5A, add NC, subtract list C, and add the starting address of program A. This indicates the relocation, while other two indicates linking information. It's very important. I have highlighted this in yellow, indicating that the value that is inserted for list A is only a relative value, not the actual value. Actual value is obtained by getting the once the actual starting address for program A is obtained. So at the time of linking, the actual starting address for program A has to be added to list A. Moving further, reference 7 generates for reference 7, the initial code generated is 1,4, which is placed in the text record immediately following 3F. So 1,4 has been placed immediately following 3F. And how many modification records are required? 1,4 is actually NA minus list A. Now two modification records are required, one indicating subtract NV, other indicating add list B. Minus of minus is plus, so add list B, and the location here is 5D. So at the location 5D, add list B and subtract NB. Moving further, the last instruction is FFFFC0, which has to be placed immediately following 1,4 in the current text record. So FFFFC0 has been inserted into the text record, and two modification records are required, one indicating the value of list B to be added because it indicates the linking information. List B is not defined in the section, and the value here encoded is 2's complement of list 0040. However, as we had seen earlier, this is just a relative value, so actual value of list A is obtained by adding the starting address for program A. So this is again an example of linking plus relocation. So add list A and subtract program A, because we have minus list A, so it is add minus program A. So that is all regarding the generation of object program for program A. Now we will proceed with the generation of object program for program B. The starting address is 0, length is 7F. So when the first statement is processed, that is the start statement is processed, header record is generated with the length and the starting address. Next, the defined record is generated corresponding to the xdef statement, two symbols are list B and NB, and the values are 60 and 70. So they are generated. Then the xref statement is processed, and all these symbols are listed in the refer record. So you may see that all the symbols are listed. Thereafter, the remaining statements are processed, and the first object code begins at the address 36. And please note here, all those statements which are underlined involves external references, and there is a reference to the symbol list A here. In program B, list A is not defined, so this is an external reference, and you have seen that the object code generated is using the 4-byte format, and the address field is 0 because we don't know the value of list A. So having placed this object code into the text record with the address 36, one modification record has to be generated, indicating that the value of list A has to be added at the location where zeros are placed. Where are zeros placed in the memory? Please note the instruction begins in the address 36, and the address field will begin in the next location, that is 37. So after placing this into the text record, we need to generate a modification record saying list A has to be added at the location 37. So we have placed the object code in the text record with the starting address 36, and we have included a modification record saying that list A has to be added at the address 37. Please note this is an instruction operand. Operand is 5 half bytes in length because address field is 20 bits. Moving further, the next statement is LDT list B plus 4. This instruction can be completely assembled. There is no underline, meaning that there are no external references. So a program counter relative mode is used, and the generated code is 772027, which is placed in the text record immediately following 031000000. So you may see this has been placed immediately following the previous code. No modification records are required. Moving on to the next, this is an external reference because end A and list A are not defined in program B. So initial code generated is here. The address field has to be modified by adding the value of end A and subtracting the value of list A. So this modification has to be done at the location. Please note the instruction itself is loaded at 3D. However, the address field begins at 3E. So the modification record should indicate the address where the modification is to be done is 3E. So at 3E, add the value for end A and subtract the value of list A. Add the value of end A, subtract the value of list A. Moving further, we have a series of instructions. So the current text record can be ended here. We have ended the text record with the length. So this is 4 bytes, 4 bytes and 3 bytes. So 4 plus 4, 8, 9, 10, 11. 11 bytes is B in hexa. Next, we will write the new text record for the remaining codes. The object code generated is 0, 0. None of the values are known. So we need to generate 3 modification records, and the address is 70. So initial value 0 is inserted with the starting address 70. 3 modification records saying that end A has to be added, list A is to be subtracted, and list C to be added. End A, list A, list C. So this is corresponding to the instruction marked reference 4. Proceeding ahead, the next code generated is FF6 placed immediately after 0. So we have kept this immediately after zeros. And how many modification records are required here? 2 are required because the value assembled here is -10. NC and list C are unknown, so 2 modification records are required. So NC and list C, and the address is 73. Moving ahead, the next reference 6, that is the object code generated is initial value generated is 6 Fs, which indicate -1. None of the values were known in the program B during the assembly time. So 3 modification records have to be generated with the address 76. So 3 modification records have been placed, NC minus list C plus list A. And please note the object code itself is placed immediately after F6 in the text record. So after F6, the object code itself is placed and 3 modification records are generated. Proceeding ahead, the next code is FF0, which corresponds to reference 7. Here end B list B is known, however end A list A are not known. So this part was evaluated and this is the initial value. So two modification records are required indicating end A to be added and list A to be subtracted. So two modification records and the address here is 79. So you may see that two modification records are generated and the object code itself is placed in the current text record. Proceeding ahead, the last object code has to be placed into the record, which is 60, placed immediately after FF0. So we'll see it is placed here in the text record and the two modification records are generated. What do they indicate? One is subtract the value of list A because list A is not defined in program B. So subtract the value of list A. But there is one more record. I have highlighted it in yellow because it indicates program relocation, because list B is defined, its value is 60. However, this is only a relative value. Actual value is obtained by adding the starting address for program B. So add the starting address for program B and the location here is 7C. So that is all with respect to the object code for object program for program B. Finally, when the end statement is processed, when the end directive is processed, the end record is placed. Only if the end record specifies a label, then the corresponding value has to be inserted in the text record. Moving on to the program C. The program begins at the address 0, length is 51. So first the start statement is processed and the header record is written, length is 51. Thereafter, symbols in xdef statement are entered into the defined record with the address 30 and 42. So 30 and 42 symbols are list C and end C. Thereafter, xdef statement is processed and all symbols are entered. Symbols are list A and list B and B. The remaining statements are processed. The first object code generated is for LDA list A, which is 031000. Please note all of these instructions involves external reference. So list A is not known, so we need to have one modification record corresponding to list A, whose value has to be inserted at the location 18 plus 1, that is at the location 19, because this is 18. At the address 18, location 18, we have 3. Address begins at the next location, that is 19. So write a new text record which is written here. The starting address is 18 and in the modification record we need to indicate that list A has to be added at the location 18 plus 1, that is 19. So 19, add list A. The length is 5 half bytes because this is a 4-byte instruction and the address field is to be modified. Next, moving on to the next, the code generated is again a 4-byte object code. List B is unknown. Only 4 was assembled. So one modification record saying value of list B to be added at the location 1C plus 1, that is 1D. So we have placed the object code in the current text record and one modification record saying that list B has to be added at the location 1D. It is 1C plus 1, that is starts from this location. Moving further, the third object code is 051000. Again here, none of the values are known, so zeros are inserted. Two modification records needs to be generated, one for end A and the other for list A. And the modification is to be indicated at the location 21. So at the location 21, add end A and subtract list A. The object code itself is placed into the text record. Next, remaining statements are processed, and since this is the end of the text record, there are few instructions, so we terminate here and you may see that there are 4, totally 12 bytes, so which is indicated here. The length is C. We'll proceed with the next object code, that is 30 corresponding to reference 4 generated at the location 42. You may see that here the value for list C is known because this is program C and it is 30, but this is a relative value, so we need to add the starting address for program C, so which is indicated with the yellow here, meaning it's example for relocation. So two modification records indicating linking and another indicating relocation. 3 are required and the address here is 42. So at the location 42, add end A, subtract list A, add end A, subtract list A, and list C is already assembled. However, this is a relative value, so add the program address for list. for the current corresponding control section. So add the program starting address for control section to get the actual value for list C. Proceeding ahead, the next instruction is 000008 that is generated. This is a constant, and in this case all of the expressions were evaluated. Entire expression was evaluated because end C and list C are defined in the same section. So the object code is placed into the text record. No modification records are required. Moving on to the next, that is reference 6. The object code is 000011, which is actually NC minus list C minus 1. However, list A is not known. So one modification record is required for list A. So we have added one modification record. The object code 11 has been placed into the text record following 08, and one modification record indicating the address 48. So one modification record has been placed. Moving further, the reference 7 is processed and the code generated is 000000. Address is 4B. So this is to be inserted into the text record following 11. So we have inserted it. How many modification records are required? We need 4 modification records because none of these values were known at the assembly time. So the 2 should indicate that first 2 indicating end A to be added, list A to be subtracted. Thereafter end B to be subtracted, list B to be added. So 4 modification records with the address 4B. So this is corresponding to reference 7. Next, proceeding with the last one, that is reference 8. The instruction here involves an operand list B minus list A. Both symbols are unknown. So zeros are inserted. So we place the object code here at the end. I have missed highlighting it. So last code is placed in the text record, and the modification records to be generated are corresponding to location 4E, add list B and subtract list A. Add list B, subtract list A at the location 4E. So that is all. Then the end statement is processed, so end record is generated. So this is all with respect to processing of the control sections which involve external references by assembler in pass 1 and pass 2. So I suggest that you go through the object code generation as well as the object program generation exclusively in each of the control sections and understand how each of the object codes are generated differently in different sections and how the modification records vary from one control section to another accordingly. So we are done with the issues of program linking from the perspective of assembler. We have seen how the assembler handles independent control sections and how it generates the object code when an instruction involves reference to a symbol defined in another section. Now, having generated the object program, having generated independent control sections or independent object programs, now we need to see how a linking and a relocating loader processes this object program and loads the object codes into memory and performs the linking and relocation. So I will be discussing the functionalities of linking and relocating loader and see how relocation and linking is performed along with the basic functions of loading the program in the next video lecture. Thank you.